Okay, y'all, this is the key to quiz 14. Alright, so for these heat flow problems, you get to use this formula. Okay. So we need to know, well, so K is given, but we need to get the gradient of U. So that's relatively straightforward. Derivative with respect to x is 0, with respect to y is 10y, and with respect to z is 10z. Alright, now we have to think about this surface right here. Okay. We have to, in order to be able to do this kind of surface integral here, this is a surface integral. We need to be able to get a parameterization of that cylinder. And it looks to me like the base of it, so to speak, would be a circle of radius 7. So if we were going to parameterize that, I better not use U since we already used it. So if you think about what this thing does, X, Y, Z, it kind of goes like this. It's the axis of the cylinder is the x-axis, and it goes from 0 to 4. That's what's going on with this thing. So I guess x could be one of the parameters, and then theta could be the other one. So the x component is free, and then since this is a circle or radius 7, I'm just going to use this to be the cosine and this to be the sine, because it's the vertical. So radius cosine theta, radius sine theta. Okay, and ultimately the formula we're going to be using is in order to do this surface integral of delta U ds, we want to use the equivalent form, the region in the xy plane. And then what you do is you do delta U of your R. Okay, you plug this kind of into your delta U. Then you want to dot product that with the cross product of your partial derivatives, but it's going to be with respect to x and with respect to theta, and then over the area of this domain. So we need to get these partial derivatives to be able to do this. So the partial with respect to x would be 1, 0, 0, and the partial with respect to theta is 0 minus 7 sine theta, and then root 7 cosine theta. So we got to do a cross product of them before we can apply this thing. So okay. Alright, so we're getting nothing in that component. In this one, we're getting the negative of that. And then in this one, it's that product. So that is that part right there. So we're going to dot this with delta U evaluated at R. Okay. So let's go ahead and do a different color just so we know what we're doing here. Okay, so this guy right here would be, okay, well that's just 0. So delta U of R is just 0 there, but 10 times the Y component, so that would be 10 root 7 cosine theta. I'm out of room here. And then 10 root 7 sine theta. Okay. That thing gets dotted with that thing. And then you integrate over your region now. So the x will run from 0 to 4, and then the theta goes 0 to 2 pi. So that's how we're going to set that region up. So it's kind of separating this all off. If we dot these, so 0, and then that would be negative 70 cosine squared theta. And then that would be negative 70 sine squared theta. Okay, which is just negative 70. Okay. Now remember, let's not forget our negative k was there. Okay. So if I pull out this negative 70 and hit it with this negative k, what is that? Negative 70 times negative k, 315. So I have this negative 4.5 out here. I don't want to forget about that. So we have our negative k on that in general. Okay. Anyway, 315 brought the negative 70 out, so then it's just 0 to 2 pi d theta, and then 0 to 4 dx, because there's nothing left in there. So I'd multiply 2 pi by 4 by this, so times 2 times 4, I end up getting 2520 pi. That's my final answer. Okay, so that was kind of complicated, but I think it worked out. For this Stokes theorem, the basic Stokes theorem says that the contour integral of a vector field is the same as the surface integral of the curl of that vector field. So sometimes it's good to turn the curl into the main one, or the main into the curl. And since it's asking us to find this, we need to turn it into a curl. So we're going to have to find the curl of f. So curl of f is defined to be del cross f. So partial with respect to x, y, partial with respect to y, 5z, partial with respect to z, 7y, I, j, k. Okay. What is this thing? That's 7 minus 5, so that's 2. That's 0. subtracting x, but oh wait, you go like this, 0 and 0, so that's nothing. Then you go like this, which is 0, and then you subtract an x, so it would be just like this. So that's the curl of f. Alright, so we now know what it is that we're doing. So C was the curve of intersection of this plane and this cylinder. But since we can convert it into a surface integral, then that actually lets us do it over the domain in the xy plane. So what domain in the xy plane is it? Well, this thing here's a vertical cylinder, right? It hits this plane, it's going to hit it in like an oval shape, but then when you project it down, it'll just go straight down into the xy plane as a circle of radius 12. So that's what the domain would be. So the radius would go 0 to 12 and theta would go 0 to 2 pi. And then there's a formula that since the above thing here is just a function, right? Because you could actually solve that like this. So this is like our g of x, y. Okay. And there's no y in it. It's a straight up function, so we don't actually have to use a parametric surface to do this. There's a simple formula that lets us do it, where you go over the domain in the xy plane, which is just the circle, and then it was negative p, and then the derivative of g with respect to x, and minus q. Now these p and q's and r's are referring to these, to these. Partial of g with respect to y, and then plus just r. Okay. So, what do we got here? Negative p, negative 2. So, negative 2. What's the partial of g with respect to x? That would be negative 1. Then q times, well, partial of g with respect to y was 0 anyway, so then plus r, that would be negative x. Now since this is a circular domain, we need to convert this. So this is 2 minus x, so what this is really going to be radius 12, and then it's 2 minus x, so that's 2 minus r cosine theta, r d theta. Okay. So 2r would become just r squared, and then minus r squared cosine theta would become minus a half, or minus a third, r cubed cosine theta, evaluated from r is 0 to r is 12 d theta. So putting 12 in there is 144. Putting 12 in here, what's 12 times 12 times 12 divided by 3? So it's minus 576 cosine theta, because the 0 didn't do anything. Alright, So this is 144 theta minus 576 sine theta, evaluated over 0 to 2 pi. Now obviously sine theta is 0 at both of these, so that's gone. So you just put a 2 pi on that, so it would be 288 pi. That's the line integral of those crazy things. Okay. Now we have to use the divergence theorem. The divergence theorem says that you can turn a surface integral of a vector field into a triple integral over the region enclosed by the surface. So as long as it's a completely enclosed region, which it is, right? If you read this description, it's a box. So this applies. Then you just do the divergence of F over the volume. Okay, so we'll just get the divergence of F. So divergence of F equals the dot product of like this. So we're doing that dot product, and then we're going to integrate it over E. So the partial of, okay, that's just y e to the z. That drops a 2 down. And then this one is the same, it doesn't change. And then we have cancellation, so it's just 2xy e to the z. That's the divergence of F. So now we're going to do the triple integral. Now, it really doesn't matter since it's a box. I'm just going to go x 0 to 9, 0 to 6 on y, and then 0 to 1 on z. And then we're integrating this thing. And I want z, y, x. These things are all completely independent of each other now, so it's just 2 integral 0 to 9 x dx integral 0 to 6 y dy integral 0 to 1 e to the z dz. I think that's, oh no, wait a minute, I miswrote that. That's z to the third. Good thing I caught that. Yeah. So does that make sense? Okay. So this is going to be 2 and then 9 squared over 2, so times 81 over 2, and then I think that's right. And then yeah, this would become 36 over 2, I think. It's y squared over 2. This is z to the 4th over 4, so that would be times 1/4. Okay. So I don't know what that is. 81 times 36 divided by 8, it looks like. I think that's it. Let me just check. X went 0 to 9, Y went 0 to 6, Z went 0 to 1. 2 popped out, X, Y, Z to the cube. Looks right to me. So X squared over 2 from 9 to 0, 6 to 0, 1 to 0. So, yep, 81 times 36 over 8. Okay, then there was an extra credit problem. Need to show that these things are equal. So I'm going to start with the left-hand side. So this is the directional derivative. If you remember, and this is in the direction of the normal vector. So what that is you take the gradient of f and dot it with the direction vector. Okay. And this is precisely where the divergence theorem would come in. Because this thing right here, you know, it's exactly when the divergence theorem kicks in. It's the same as this kind of thing. So, okay, it would be the divergence then of the vector field then over the volume. And then what's divergence? That's dotting the vector field with del. And then this thing is del squared f dv, which is what we want to show. So that's really all you needed to do. If you look in the section, if you look at the beginning of the section, this and this are the same. Like that's basically what the section is saying. And if you look at the surface integrals, you can see that this kind of thing is the same as this kind of thing, right? Dotting it with ds is like it's like doing that. So, okay, thanks for watching.